You know, computers only speak in zeros and ones, right? It's all just on or off. So how in the world do they represent something like a negative number? I mean, if all you see is on and off, how do you even begin to understand less than zero? Well, that's exactly what we're going to break down.
So let's just put the question right out there. When you type in -5, what does the computer actually see in its memory? What's the pattern of ones and zeros? It's a really specific puzzle, and by the end of this, you're going to know exactly how it's solved.
Okay, so before we can tackle the tricky stuff, the negative numbers, we've got to start with the easy part, positive numbers. This all begins with something called an unsigned number.
Unsigned numbers are basically binary at its simplest. Think of it like this. Every single bit is just there to add to the number's total value. There are no hidden meanings, no secret codes for signs. It's just pure number. So if we're looking at a standard 8-bit number, and we use all 8 of those bits for the value, we can count from 0, which is all zeros, all the way up to 255, which is all ones. It's a perfectly good system until you need to, subtract or deal with debt or freezing temperatures.
And that is where the whole game changes. To handle negative numbers, we have to make a sacrifice. We take that very first bit on the left. It's called the most significant bit, or MSB, and we give it a totally new job. It's not a value anymore, it's a sign. A 0 means the number's positive, and a 1 means it's negative.
Okay, so we've decided to use 1 bit for the sign. Cool. But what about the other 7 bits? How should they represent the number? Turns out, people came up with a few different answers to that question. Let's look at the 3 big historical methods.
All right, method number 1. This is the one that probably pops into your head first. It's called sign magnitude, and the logic is super intuitive. You just use that first bit for the sign, and the rest of the bits just represent the number's size, or its magnitude. Simple.
So if we want to write -5, it's pretty straightforward. You just flip that first bit to a 1, that means negative. And then, in the other 7 bits, you just write the number 5, which is 000000101. Slap them together, and you get this. Makes perfect sense, right?
So that was one way to do it, but then came another idea, one's complement. The logic here is also pretty simple, just in a different way. You start with a positive number, and you literally just flip every single bit. All the zeros become ones, and all the ones become zeros.
Let's stick with our example, the number 5. Positive 5 is 000000010. Now just flip everything. That gives you 11111100. And in the world of ones complement, that's -5. You can see it's a totally different binary pattern than what we got with sign magnitude.
And that brings us to method number 3, the big one, 2's complement. Now this one's a little two-step dance. First, you do the exact same thing we just did in 1's complement. You flip all the bits. But then there's one extra little step. You add 1 to whatever you got.
So let's go back to our -5. We take that flipped version from before, the 11111010, and we just add 1. That gives us 11111011. So, now we have 3 completely different ways to write -5. The big question is, which one won? And more importantly, why?
All right, so we've got 3 contenders, but there is a clear winner, a total champion. It's 2's complement. I mean, pretty much every modern computer, phone, and toaster you've ever used relies on this system. The reason it won is not just clever, it's kind of beautiful.
Let's just do one more quick example to really nail this down. How about -17? First, you write out positive 17 in binary. Easy enough. Step 2, invert every single bit. And step 3, the final touch, just add 1. And there you have it, 11101111. That is how a computer sees -17. But again, why this extra step? So what's the big deal? Why go through all that trouble of flipping bits and adding 1? Well, the secret isn't just about storing numbers. The real magic happens when you start doing math. Think about this, 9 minus 5. Super easy for us, right? But for a computer, building a circuit that actually does subtraction is way more complicated and expensive than building one for addition. So the engineers thought, what if? What if we could get rid of subtraction altogether?
And this is the genius of 2's complement. The computer doesn't have to learn subtraction. It just turns every subtraction problem into an addition problem. Instead of calculating 9 minus 5, it calculates 9 plus -5. And since we have this great way to write -5, it can just use the simple addition circuits it already has.
Okay, let's watch this in action. Here's our positive 9 in binary, and here's our negative 5, using our fancy 2's complement method. Now all the computer has to do is add them up, bit by bit, just like any other binary addition problem. So we add them up and... Whoa, hold on. We started with two 8-bit numbers, but our answer has 9 bits. See that little extra 1 that carried all the way over to the left? Looks like something went wrong. Did we break it?
Nope. This is actually the coolest part. See, the whole system is cleverly designed to work inside an 8-bit box. That extra 9th bit, which is called an overflow or a carryout, it just falls off the edge. It's outside the box, so we can just ignore it. And when we look at what's left inside our 8-bit box, 0000100, what is that? It's 4. It worked perfectly. 9 plus negative 5 equals 4, and we did it all without a single subtraction circuit. That is why 2's complement is king. It's just so efficient.
Okay, so we've seen how it's done and why it's so clever, but let's bring this back to the real world. When does a programmer actually have to think about this stuff? When does it really matter?
Well, it's a huge deal, actually. It's a fundamental choice you have to make. You use unsigned numbers for things that logically can never be negative, like a memory address or an item's position in a list. You can't have the negative 5th item. But for pretty much everything else, like money or temperature or scientific data that goes up and down, you absolutely need signed numbers. And 2's complement is the system that quietly makes it all possible.
And I want to leave you with one last little brain teaser. Because of the way 2's complement works, in an 8-bit system, the range of numbers you can represent is negative 128 all the way up to positive 127. Did you catch that? There's one extra negative number. It's this tiny, weird asymmetry baked into the foundation of almost all computing. So what does that say about how computers model our world? It's just something to chew on. Thanks for watching.